pH is often a difficult topic for students. pH is the measure of acid concentration, and acid is determined by the hydrogen ion. This is the hydrogen ion, H+. It is merely a hydrogen atom that has lost one electron. And these hydrogen ions are very dangerous when they build up in the body. They're created by many metabolic processes, and they're very reactive. So if you took water and separated it, you would have one hydrogen ion, H+, and one hydroxide ion, OH negative. Here's water dissociating into the hydrogen ion and the hydroxide ion. The pH is critical. Homeostasis must maintain our pH in a very, very precise way. You can see the pH of some substances. Of importance to us is the pH of blood. It's slightly basic. So neutral has a pH of 7, and 7 to 14 is basic, and below 7 down to 0 is acidic. The smaller your number gets, the more acidic you become. From one number to the next, it's a logarithmic scale, so it's 10 times the difference. So a pH of 3 is 10 times stronger than a pH of 4. And the pH of blood, you can see, normally ranges from 7.35 to 7.45. Slightly basic. Things that are very, very acidic, our stomach acid is very acidic. Foods we eat are acidic, such as coffee, orange juice, tomatoes, pickles are acidic. Basic things, our house cleaners are basic. Household bleach is very basic. Its bases are slippery, and acids taste kind of tart. So here you have ammonia, oven cleaner, bleach is basic. Pure water is neutral. Urine, the pH of urine depends on your health, your state of health. It will change from day to day depending on what you're eating, medications you're taking, and so on. What is the normal blood pH? It was 7.35 to 7.45, or slightly alkaline. Alkaline is another word for basic. So strong acids are like hydrochloric acid. When you put hydrochloric acid in water, it completely dissociates. That is, it's going to break down to its two ions completely. So you'll have water with lots of hydrogen ions and chloride ions. That is the signal of a strong base, one that completely dissociates. So you can imagine a weak base is one that would not dissociate completely. We have strong acids such as sodium hydroxide, a strong base, and it's a strong base because it releases the hydroxide ion completely when it's added to water. Strong bases dissociate completely. Carbonic acid is a weak acid, but we'll see it's really important in our body. It's really important in the respiratory chapter. So this is carbonic acid, H2CO3, a weak acid, and it reversibly dissociates into the hydrogen ion and the bicarbonate ion. You might recall bicarbonate, sodium bicarbonate is baking soda. So sodium bicarbonate would be NaHCO3. Weak acids and weak bases fail to dissociate completely. Sodium chloride, an ionic compound, dissociates completely. But salt is, when we think of salt, we think of table salt. But truthfully, a salt is a chemistry term, and it consists of an ion that has a positive ion and a negative ion, a cation and an anion. Don't worry too much about that. When we talk about salt, we really mainly talk about sodium chloride. Now, buffers are really important in the human body. If our pH were to go too low, we'd be in trouble. If our pH were to go too high, we'd be in trouble. We've got to maintain stability in that pH, and that's what buffers do. Buffers usually involve a weak acid and its related salt. So here's the weak acid, carbonic acid, and here's its related salt. I think probably at this point just memorize that a buffer involves a weak acid and its salt. Organic compounds are compounds that contain carbon and hydrogen. And you know, if you've got a lot of compounds that contain carbon and hydrogen, you think they'd be quite similar to each other. But if you tack on a few atoms, specific atoms, it changes the nature of that compound. And that little group of atoms is called a functional group. For example, here are some functional groups. The ones you have to know would be carboxylic acid, carboxylid or acid. The carboxylic group is the acid functional group. So that's COOH. Now this shows you what it looks like. There's a carbon with a single bond to OH and a double bond to oxygen. Not that important. COOH is more important. It acts as an acid. So if you have a huge molecule with lots of carbons and hydrogens, and one of these functional groups, the carboxylic acid group, added to it, it becomes an acid. This is the amino group, NH2. We find these in amino acids. The hydroxyl group, OH, we saw that when we dissociate water. Phosphate group, we'll see the phosphate group with ATP, our high energy compound. So when you have a functional group, this right here represents the functional group, COOH. R represents the rest of the molecule. Which of these is the name for the chemical group NH2? You got to memorize those functional groups. That would be B, the amino group. Carbohydrates are the first nutrients we're going to talk about. Carbo refers to carbon. Hydrate refers to water. It contains carbon, hydrogen, and oxygen, right there, in a ratio of 1 to 2 to 1. 1 carbon to 2 hydrogens to 1 oxygen. So the 2 hydrogen and the 1 oxygen refers to the hydrate or water, carbohydrate. And examples are sugars and starches. And these are important energy sources in our body. Glucose is probably the most common simple sugar. It's called a monosaccharide or single sugar. You can represent it with this kind of structure or this closed structure here. You won't have to recognize these. You won't have to memorize these. We're just showing you a little bit how these atoms are laid out in that molecule. Another example of a monosaccharide is fructose. Glucose is our universal cellular fuel. Fructose is fruit sugar. It's sweeter than glucose. It has the same formula, but those atoms are laid out a little differently. And that's called an isomer. A molecule with the same molecular formula but a different structure is an isomer. Glucose and fructose have this formula. You might as well memorize C6H12O6 right now because you're going to see it forever. That's glucose, our universal cellular fuel. But fructose has the same formula. It's just a different structure. So if we put two of them together, a monosaccharide and a monosaccharide, we will have a disaccharide. And this example is sucrose. Sucrose consists of 1 glucose and 1 fructose. They are joined together in a synthesis reaction, and of course it's dehydration synthesis where we have to pull out a water molecule. If you were to go in the other direction and break it down, it would be hydrolysis. Sucrose is table sugar. A polysaccharide would be many monosaccharides together. Usually that monosaccharide is glucose. For example, the starches are made in plants and only plants. For example, in potatoes and in rice grains. Those starches are made up of many millions of glucose molecules. But animals can also make a polysaccharide. Animals eat starch and then store excess glucose in the liver as glycogen. So when an animal requires more blood glucose, it breaks down the glycogen in the liver and the muscles to supply the glucose. Each circle on this molecule represents a glucose molecule. So here's our glycogen. It's a storage form of glucose in animal livers. And there's just millions of them. You've probably heard of complex carbohydrates. Well, complex carbohydrates are more difficult to break down in the body. They break down more slowly. They influence our blood glucose levels differently. So simple carbs would be like disaccharides like sucrose, or monosaccharides like glucose and fructose, all that high fructose corn syrup and Coca-Cola. Those are simple carbs. They allow the glucose levels to increase very rapidly in the blood, and they're very bad for our health. Which of these is a monosaccharide? I hope you recognize glucose. Sucrose is a disaccharide, it's table sugar. Glycogen is a polysaccharide, it's made in the liver. And maltose is a disaccharide. When we start breaking down starch in our mouth, it forms maltose. Which of these is not made from glucose? Fructose is a different monosaccharide than glucose. Therefore, it is not made from glucose.